Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 8, lecture 8, in which we will address the next 5 theorems, the theorems numbered 32, 33, 34, 35, and 36, and across these 5 theorems in the very first 3 theorems, the theorems numbered 32, 33, and 34, we will prove that the magnitude of the angle between any two straight lines, regardless of their position with respect to the center of inversion, under the corresponding inversion of the real plane with respect to a circle, is preserved. Once we generate these 3 proofs, we will pretty much automatically get the proofs for the following 2 theorems, the theorem number 35 and the theorem number 36, which make a very similar fearless prediction about the magnitude of the angles between any 2 circles under an inversion of the real plane with respect to a circle with both powers, positive and negative. Why is that? That is so because according to our definition number 4, we will define the angle between any 2 cooperating planar curves as follows. Let us assume that C1, shown in green over here, is a planar curve that is at least once differentiable, let us say, on a certain subset of real numbers, or more pedantically, at least once differentiable at the point of interest, and let C2, shown in blue over here, be yet another planar curve that is also at least once differentiable on a certain subset of real numbers, or more pedantically, at least once differentiable at the point of interest. And then, under these conditions, we define the angle between the curves C1 and C2 to be the angle between the tangent straight lines that are drawn to these curves through the point that these 2 curves have in common, such as the sample red point shown over here. In other words, in plain English, if we have 2 smooth enough curves, smooth enough means that the curves should be continuous at the point of interest, but continuity is not enough. We demand that the curves are not only continuous, but they're also at least once differentiable at that point. And that means that both of these curves admit the existence of the limiting position of a second to both of these curves at the point of interest, or both of these curves possess the so-called tangent straight lines, such as the tangent straight line tau 1 shown over here in green, and the tangent straight line tau 2 shown here in blue. And precisely it is the angle between these 2 straight lines is what we take to be the angle between 2 such cooperating curves. Now, the proofs that we will generate for the theorems 32, 33, and 34 will do all the heavy lifting, and they will address precisely the magnitude of the angle between any 2 straight lines under the corresponding inversion with respect under the corresponding inversion of the plane with respect to a circle with both powers, positive and negative. And once we prove these theorems for straight lines in isolation are just that, straight lines, but after these proofs we can inflate, so to speak, the meaning of any 2 straight lines to be what? To be the tangent to 2 cooperating curves, continuous and at least once differentiable. And among such class of curves, a circle is certainly such a curve. Now, in the upcoming proofs, we will need the following very basic elementary material, and because I do not want to spend more time than I have to on discussing the details of these theorems, we will go over them right now. In the upcoming proofs of the theorems number 32, 33, and 34, we will need the Euclid's Elements Book 1 Proposition 27 shown over here, Book 1 Proposition 29, Book 1 Proposition 30, and the so-called Playfair's axiom. Now, in detail, let us say we have one straight line shown in yellow over here, falling or intersecting, if you will, two distinct straight lines. All of these straight lines evidently belong to one and the same plane. And let's say one straight line is called L1. It is shown in blue on top. The other straight line is called L2. It is shown on the bottom over here. And then, according to Book 1 Proposition 27, if under the given setup the so-called alternate angles alpha and beta happen to be equal one another, then Euclid proves in Book 1 Proposition 27 that from that equality of the angles, of the alternate angles alpha and beta, it follows that the straight lines L1 and L2 at hand are parallel, shown with the symbol by two vertical straight lines. In other words, if, in plain English, alpha is equal to beta, then L1 and L2 are parallel. Book 1 Proposition 28 in Euclid's Elements is a minor variation on Book 1 Proposition 27. We will not need that, but we will need the next theorem, Book 1 Proposition 29, which is the converse of the Book 1 Proposition 27. And that theorem basically states that if the straight lines L1 and L2 are known to be parallel, then the straight line shown here in yellow that is falling on them will make the alternate angles alpha and beta equal one another. In other words, in the if P then Q form, in the traditional form of an implication, if L1 is parallel to L2, then alpha is equal to beta by magnitude, of course. In Book 1 Proposition 30, shown over here, Euclid in some sense encodes the so-called transitivity of the binary is parallel to relation. In other words, in Book 1 Proposition 30, Euclid proves that if a given straight line A and a given straight line B are known to be parallel to one and the same straight line named C, then from this premise it follows that the straight lines A and B are themselves parallel. Lastly, it is an option in some sense, but I would like to throw it in. You probably have heard about this axiom just because it is quite popular, especially in middle and high schools, but you probably or maybe not have heard about the fact that this axiom has a name, and it is called the Playfair's axiom. As such, according to the Playfair's axiom, in Euclidean geometry, through a point P, shown in red over here, that does not belong to a given straight line L, shown in blue over here, there passes one and exactly one straight line, lambda, shown in green over here, that is parallel to the given straight line L. Now it pays, again, before we deep dive into the corresponding proofs, you want to make sure that you have a firm grasp on these three basic theorems of Euclidean planar geometry. And now across the theorems 32, 33, and 34, we will prove that under an inversion of the real plane with respect to a circle with both powers, positive and negative, the magnitude of the angle between any two straight lines is preserved regardless of the position of these straight lines with respect to the center of inversion. And again, as usually we do it, we will drag these two straight lines first through the center of inversion, and then we will gradually peel them off the center of inversion, and we will see what happens if none of the straight lines pass through the center of inversion in the theorem number 34, but we will start with the theorem number 32, in which both of the given straight line will pass precisely through the center of inversion. According to the theorem number 32, under the inversion of the real plane with respect to a circle named C that has the point O as its center and R, a strict positive real number, as its radius, any two straight lines, L1 and L2, each of which pass through the center of inversion, and that premise is encoded over here with these symbols. The point O belongs to the straight line L1 and the straight line L2. So under this premise, under the inversion with both positive and negative power, the magnitude of the angle between the straight lines L1 and L2 is preserved. In other words, the angle between the pre-images and the angle between the images under the given inversion for the given objects will remain one and the same, and the magnitude of the angles I portray over here with the absolute value sign with the vertical bars, because we know that in modern times we assign at least two parameters to every planar angle: the magnitude and its orientation or direction. Usually we measure positive angles counterclockwise and negative clockwise, and as such we already seen with the fundamental theorem of inversive geometry that we proved in the previous lecture. We know that the inversion of the real plane with respect to a circle, whether this inversion is carried out with positive or negative power, preserves the magnitude of the angles, and it changes the orientation or the direction of the relevant angles to their opposites. That is why inversion of the real plane with respect to a circle is called, as a mapping of the plane into itself, is called anti-conformal, because conformal mappings, they preserve both, not only the magnitude but the orientation or the direction. As such, in all the upcoming theorems 32, 33, 34, 35, and 36, when I say the angle, I of course mean the magnitude of the angle, because the moment we start paying attention to the orientation or the direction, we already know from the fundamental theorem of inversive geometry, the so-called similar triangles theorem, the theorem number 23, that the magnitude is preserved but the orientation or direction is flipped to the opposite. As such, for a proof which is very straightforward, we observe that actually what we do here is indicative of how you will work with all the upcoming problems that you will solve with the mechanism of inversion, and that is, you will take a certain initial mix of objects, and then you will see what other images are produced by the chosen inversion across all the objects of interest. Here the objects of interest will be, let's say, a straight line L1 shown in green that passes through the center of inversion. The center of inversion O belongs to the straight line L1, and the second object of interest will be straight line L2 shown over here in blue, and encoded over here, the center of inversion belongs to the straight line L2. And so now by the chosen inversion, I do not show the circle of inversion over here. See, I do not show its radius, but because we really do not need that, what we do need over here is we need to examine where will the chosen inversion take these objects to. And in the theorem number 9, we already proved that under either power of inversion, positive or negative, the straight line such as L1 will be taken into its image L prime 1, which will be the original straight line L1 itself. And by the same theorem 9, the straight line L2 under the inversion of the plane with respect to a circle, whether the power of that inversion is positive or negative, that straight line will be taken into its image named L prime 2, which again will be precisely the straight line L2 itself. Again, we prove these statements in the theorem number 9. Remember that when the power of inversion is positive, then we have exactly two stationary points on the straight line. These are the points where the circle of inversion and the given straight line intersect. And when the power of inversion is negative, then there are no fixed points on a given straight line. The entire straight line gets rebuilt in a non-trivial way, but either way, when the power of inversion is positive or negative, our straight lines get rebuilt pointwise, point by point, into themselves. As such, if theta is the angle between the pre-image straight lines L1 and L2 under the chosen inversion, this straight line will be essentially taken into themselves, which means that the angle between the images of the straight lines L1 and L2 will be precisely theta again, which basically proves that the magnitude of the angle between the pre-image straight lines L1 and L2 under the inversion of the real plane with respect to a circle with both powers, positive and negative, is preserved. Again, I want to emphasize one more time that here, when we're discussing all these theorems, what is preserved is the magnitude. And I capture the magnitude with the absolute value sign just to make sure that this is the characteristic, the property of an angle that is captured. If we carefully play out the angles, which are in this case will be positioned in some interesting way. If we take out the pick points on our straight lines and then invert these points, this is precisely what we did in some sense in the theorem number 23. We will see, as we explained in the proof of the theorem number 23, the magnitude of the angle theta here will be the same, but its orientation or direction will be changed to its opposite. According to the theorem number 33, under an inversion of a plane with respect to a circle named C that has the point O as its center and a strictly positive real number R as its radius, under both positive and negative powers, the magnitude of the angle between any two straight lines, of which precisely one passes through the center of inversion and the other one does not, is preserved. Now here, for a proof of the theorem number 33, we do exactly the same thing as we did in the proof at the beginning of the proof of the theorem number 32, and this is what you will be doing pretty much for the rest of your problem-solving career if you will be using the machinery of inversion of the, let's say, real plane with respect to a circle. You'll be taking the initial mix of objects of interest and trolling them through the chosen inversion and then examining exactly where these objects will be taken by the said inversion. Here we have precisely two objects of interest, two straight lines, and out of these two straight lines, by the premise of the theorem, precisely one passes through the center of inversion and the other straight line does not pass through the center of inversion. Here, without the loss of generality, we can assume that the straight line L1, shown in green over here, going this way, does pass through the center of inversion, O in this case. And this is depicted with the fact that the point O belongs to the straight line L1, but not L2 this time. And the second object of interest is the straight line named L2, shown in blue over here, positioned like so, just for a visual demonstration of how these two objects can be positioned with respect to each other in this case. And we already know that according to the theorem number 9, the straight line, which does pass through the center of inversion, which in this case it will be the green straight line L1, is taken into itself, and based on the theorems number 10, 11, 12, 13, and 14, any straight line that does not pass through the center of inversion, such as in our case the blue straight line L2, is taken by the inversion of the corresponding ambient plane into what? Into a circle that does pass through the center of inversion. And these two observations, the corresponding theorems, hold whether the power of inversion is positive or negative. As such, it is convenient to partition the proof of the theorem number 33 into three distinct following cases. In the first case, the case number 1, the straight line L1 is parallel, depicted with two vertical bars, to the straight line L2. In the second case, the straight line L1 is perpendicular to the straight line L2, and here the sign perpendicular basically is constructed from two bars, one vertical bar and one horizontal bar, in such a way that the vertical bar stands directly on top of the horizontal bar. And the third and the final case is when the straight lines L1 and L2 are neither parallel nor perpendicular. As such, we will begin the proof of the theorem number 33 with the first case, when the two straight lines are parallel. As such, assuming that the straight lines L1 and L2 are parallel with respect to each other, we take the magnitude of the angle theta between these two straight lines, shown with the cap over here as an improvisation on a way to capture the angle between two straight lines, is 0 radians. We seek to show in this part of the proof of the theorem number 33 that the angle between the images of these straight lines under the chosen inversion with either positive or negative power will also be 0 radians. Now we know that under the chosen inversion, whether the power of that inversion is positive or negative, the straight line which passes through the center of inversion, such as the green straight line L1, will be taken back into itself. It will be rebuilt point-wise, with the caveat that when the power of inversion is positive, then that straight line will have two stationary or two fixed points, the points where the circle of inversion, C, shown in white over here, intersects that straight line that passes through the center of inversion, O, that is the point over here. And when the power of inversion is negative, then the corresponding straight line has no stationary points, and it gets rebuilt point by point in a non-trivial fashion. Either way, that straight line is taken into itself, and when the power of inversion is positive or negative, again regardless, any straight line, such as a simple straight line L2 that does not pass through the center of inversion O, is taken into a circle that does pass through the center of inversion O. I refer to this circle as L prime 2. That circle is shown in red, and it has the center at the point Q prime. I symbolize this fact with this manipulation over here. The straight line L2 is taken by the corresponding inversion, whether the power of that inversion is positive or negative, into a circle named L prime 2, such that the center of inversion belongs to, or the circle L prime 2 passes precisely through the center of inversion. And what will follow next will be a miniature basic template, which we will twist and turn a little bit all the way through the upcoming theorems number 33 and 34, the remaining cases of this theorem. And the central character of this template is what? Is the straight line that, remember, was always helpful for the construction of the corresponding proofs of the theorems 10 through 14. And that is the so-called straight line of centers. We refer to that straight line of centers often with the lowercase p. And that is this straight line that is perpendicular to the given straight line that doesn't pass through the center of inversion, such as L2, and the straight line that passes precisely through the center of inversion O. That straight line is depicted over here visually or geometrically with yellow color, lowercase p, the center of inversion, perpendicular to the straight line that doesn't pass through the center of inversion. Why do we use this straight line? Well, in this case, because our straight line L2, the blue simple straight line L2 that doesn't pass through the center of inversion, is taken into a red circle L prime 2 that does pass through the center of inversion. Here, the only point that is in common between the image of the given straight line L1, the green straight line that does pass through the center of inversion, and the image, the circle, the red circle L prime 2 is precisely the center of inversion, then we know that by definition of one popular definition of a tangent to a circle through a point is what? That tangent is a straight line that is orthogonal or perpendicular to the radius of the corresponding circle that is drawn through the point of tangency. But that radius, Q prime O, this line segment, to which our tangent must be perpendicular, is contained by what? It is contained precisely by our straight line of centers lowercase p. You see, this is the beautiful part of using this central constructive element. If you go through the proofs of our theorems 10 through 14, you will see that this is precisely how we constructed all our proofs, right around this helper or auxiliary straight line. As such, we prove that that straight line of centers, lowercase p, must be perpendicular to the tangent named T to the image circle L prime 2 through the center of inversion, and by the construction, it is also perpendicular to the straight line L2. And what do we have now? Well, here we have now exactly the setup of Euclid's Elements Book 1, Proposition 27. Look at this. We have one straight line, lowercase p, falling on two other straight lines, L2 and T, falling on two straight lines, L2 and T, which is a tangent to the image circle through the center of inversion. And it makes the magnitudes of the alternate angles, alpha and beta, equal one another. Why is that? Well, actually, that goes quite deep into the foundations of Euclidean geometry. This is Euclid's Over here I wrote for you postulate number 4, where Euclid postulates that all right angles are equal one another. And this is precisely what we have with our right angles that play the roles of the alternate angles over here in this case. Alpha, beta, right angle, right angle, right angle, right angle, and here right angle. Everywhere actually we have right angles. And that means what? If a straight line is falling on two straight lines and makes the magnitude of the alternate angles equal one another, then by book 1 proposition 27 in Euclid's Elements, that means what? These two straight lines must be parallel one another. The straight line T and the straight line L2 are parallel. In other words, our pre-image straight line L2 is parallel to the tangent straight line to the image circle L prime 2 drawn through the center of inversion. So now we're rolling to the next step. If we have the straight line T parallel to the straight line L2 and the straight line L1, remember this is our assumption right now, the case number 1, L1 is parallel to L2, we have precisely the setup of Euclid's Elements, book 1, proposition 30 that I discussed in the opening segment of this episode. We have two distinct straight lines, T and L1. We prove that they're both parallel to one and the same straight line named L2, and that means what? That these two straight lines are parallel themselves. In other words, the straight line T is parallel to the straight line L1. This is the pre-image of the pre-image straight line L1. But we already proved that according to the theorem number 9, this straight line L1 is the same as its image L prime 1, which means that our tangent to the image circle, red circle L prime 2, is parallel to the image of the given straight line. So in some sense, we already proved right here that the angle between the images of the objects of interest, or the magnitude of the angle between the images of the objects of interest, is one and the same. Again, once the moment we see this, we see that the angle between these two straight lines is also 0 degrees. If two straight lines are parallel, we take the magnitude of the angle between them to be 0 degrees. But we can go a little bit further when make one more step, and this is precisely where the Playfair's axiom comes in handy, because look at this. What we have now is we have a given straight line, that is a straight line L2 that precisely does not pass through the center of inversion, We have a point, such as the center of inversion O, that does not belong to that straight line L2. And we have seemingly two straight lines, namely the straight line T and the image straight line L prime 1 pass through one and the same point. And we know that by the Playfair's axiom, in Euclidean geometry, one and only one such straight line passes through such a point, and that proves that our tangent to the image red circle L prime 2 coincides precisely with the image straight line L prime 1. And in this case, it makes it especially evident that the angle between the tangent tau drawn to the image red circle L prime 2 and the straight line L1 is again what? 0 radians, and that proves precisely the claim of this theorem that the magnitude between the original objects of interest and the magnitude of the angle between their images under the chosen inversion, which in this case can have both positive and negative power, is what? Is preserved. So this is again why this claim, why is this claim correct, is because we go back to our definition 4, which we showed again in the opening segment of this episode, and where we defined the angle between a circle and a straight line, again, is as the angle between the given straight line and the tangent to the given circle drawn through the point of interest. And this is precisely what we did. We constructed a tangent to the image circle through the point of interest, which in this case was the center of inversion. In the second case, when we assume that the straight lines L1 and L2 are perpendicular, that means that the angle between them is taken to be pi over 2 radians, and the goal of this case, the case number 2, is to show that the magnitude of the angle between the images of these two straight lines under the chosen inversion will be exactly the same as the magnitude of the angles between the original straight lines, which is pi over 2 radians. How do we do that? Well, again, we go back to the idea of drawing the objects of interest through the given inversion to see what the images of these objects are. We know that the image of the sample straight line L1, shown in green, that passes through the center of inversion O, will be a straight line L prime 1, which will be basically fundamentally and structurally the same as the original pre-image straight line L1. The image of the straight line L2 that does not pass through the center of inversion, shown over here in blue, L2 as a sample configuration, which is perpendicular to the straight line L1, will be again a circle that does pass through the center of inversion. That circle is shown in red over here. The center of that circle is the point Q prime. The name of that image circle is L prime 2. And again, here I depict only one sample configuration when evidently the power of inversion is positive, because the image circle is located on the same side with respect to the center of inversion as the pre-image line, but the argument will remain exactly the same even if the power of inversion were negative, and that circle would have been located in the other half plane with respect to the original or the pre-image line L2. It doesn't really matter. As such, what do we do here? Well, here also we go a little bit deeper into the foundations of Euclidean geometry. Here we have to bring in the famous postulate number 5, according to which if our two straight lines L1 and L2 are not parallel, then they will intersect. And they will intersect at a sample point. Let's say we will name that point A. I depicted this scenario over here. The straight line L1 intersects the straight line L2 at a sample point A. And again, the chosen inversion, whether the power of this inversion is positive or negative, will take that point into the point A prime, whatever it is. It doesn't really matter, but that is how, again, if we go back to the proofs of our theorems 10, 11, 12, 13, and 14, we will see that this is precisely the point A prime that will lock in, so to speak, the diameter of the image circle L prime 2, shown in red. And our proof begins with the observation that in this case we have a show of points, the center of inversion A, the point where two straight lines in question intersect A, its image point A prime under the chosen inversion, whatever the power of that inversion is, positive or negative, the point Q prime, which is the center of the image circle L prime 2, will all belong to the straight line L prime 1, which is also the same as the straight line L1. And here the fact that all these points belong to one and the same straight line means that the diameter of our image circle L prime 2 or the line segment OA prime, as I showed over here, OA prime will belong to that straight line L prime 1. And now we go back to the argument that we presented in the previous segment for the case number 1, but essentially nothing really changes much over here because, again, what is the angle between the straight line L prime 1 that passes through the center of inversion and the circle L prime 2? Well, again, going back to our definition, that angle is the angle between that straight line and the tangents constructed to the circle in question through the points of interest, or the points where the straight line L prime 1 intersects our image circle L prime 2. One such point will be the center of inversion, evidently, because the circle does pass through that center, the point O, and the other point will be exactly the point A prime, which is the image of the point where our usual suspects intersect at right angles, as shown with this symbol over here. Consequently, again, the angle or the magnitude of the angle between the image straight line L prime 1 and the image circle L prime 2 is the angle between that straight line and the tangent drawn to the image circle at the points, at the common points of interest, the center of inversion O and the point A prime. So how do we analyze this case? Well, again, we go back to what we did in the previous segment in the case number 1, and we argue that through the same Euclid's Elements Book 1 proposition 27, but this time applied twice to the tangent T drawn to the circle, image circle L prime 2 through the center of inversion. That tangent will be parallel to the straight line L2. And the second tangent, T prime, drawn to the image circle L prime 2 through the point A prime, will also be parallel to the pre-image blue straight line L2. I depicted this over here. Again, the argument is the same, except that this time the role of the line of centers, to which we usually refer as the lowercase p, is played precisely by the pre-image straight line L1 that passes through the center of inversion and its image, the straight line L prime 1. That straight line, remember again, is perpendicular to the straight line, sample straight line L2. Then corresponding angles, the alternate angles, are equal. They are right angles. All right angles by Euclid's postulate number 4 are equal one another. So the setup of the Euclid's Elements Book 1 proposition 27 are honored. That proposition applies. Consequently, both tangents to the image circle L prime 2 at the point O and A prime, these tangents T and T prime, will be parallel to the straight line L2, and that, again, if these straight lines are individually parallel to one and the same straight line, then consequently by Book 1 proposition 30, what does that mean? That means that these two straight lines, the tangent T and T prime, must be parallel across themselves. These two straight lines must be parallel. So here we have, in some sense, a trio of parallel straight lines. The straight line T, T prime, and L2 are all pairwise parallel. And finally, because of that, we bring in now Book 1 proposition 22. We switch gears a little bit, and now, because we proved that the tangents to the image circle L prime 2, T and T prime drawn through the points of interest, the center of inversion O and the point A prime, are parallel, what do we have? Well, we have a straight line such as L prime 1 falling on two parallel straight lines. And what does that mean? Well, again, by Euclid's Elements Book 1 proposition 29, we have it that in this case, the magnitudes of the alternate angles must be the same. And what are the alternate angles over here? Well, it will be this angle and this angle. But we already showed that the diameter OA prime of the image circle must be perpendicular to these straight lines, and it is contained by the straight line L prime 1. And that means that the straight line L prime 1 makes precisely what? The angles that are by magnitude are precisely pi over 2. But what does that mean? That means precisely that the magnitude of the angle between the pre-image straight lines, L1 that passes through the center of inversion, and L2, which is pi over 2 radians, is preserved because the angle between the images of these two straight lines, or again, essentially the straight line L1 itself and the circle L prime 2, is exactly the same. And again, we go back to definition number 4 and define the angle between the straight line and the circle as the angle between that straight line and the corresponding tangents drawn to the circle through the point of interest. And this concludes the proof of the case number 2. In the third and the final case of this theorem, we assume that the straight lines L1 and L2 are neither parallel nor perpendicular. It means that the angle theta between these two straight lines is neither 0 nor pi over 2 radians. It is an interesting angle theta that sits somewhere in between, let's say, these two numbers, for example. Here we again want to prove that in this case the magnitude of that angle theta between the pre-image objects will be preserved and will be equal to the magnitude between the images of these objects. And what are the images of these objects? Well, here the story is exactly the same. The image of the given straight line, one of which passes through the center of inversion. Let's say we agreed this to be a sample green straight line L1 will be the straight line L prime 1, which will essentially be exactly the same straight line that also passes through the center of inversion. And the image of the other straight line that does not pass through the center of inversion, the sample blue straight line L2, will be a circle shown over here in red, L prime 2, that passes precisely through the center of inversion. And we know how to construct that image circle using nothing but the Euclidean tools alone, a straight edge and a compass. And the way we do that is first we snap our favorite straight line of centers, lowercase p, which is a straight line that passes through the center of inversion, the point O, and is perpendicular to the given straight line L2. These two straight lines, the straight line of centers, lowercase p, and the straight line L2 will intersect at this point over here. I did not want to designate it to keep the number of material to minimum viable, but that point reflected in a given circle with a given power, be that power positive or negative, it doesn't really matter. The algorithm still remains one and the same. We reflect that point in a given circle with a given power into this point over here. Once these points are locked in, we locked in a diameter of the image circle. We cut this diameter in half, bisect it, obtain the point Q prime, and voila, we snap the image circle L prime 2, and this is what we do. The interesting case over here, the situation over here is what? Precisely because the angle between the sample straight line L1 and L2 is neither 0 nor pi over 2 radians as we had it in the previous case. We now observe what? We now observe that our image straight line L prime 1 will intersect the image circle at two distinct points, one of which will obviously be the center of inversion, the point O, and the other one will be the point, which one? Well, it will be the point A prime, which is the image of the point where our straight lines that are not parallel definitely intersect the point A. Remember, by the fifth postulate, these two straight lines will intersect. We name that point of intersection as A. Under the inversion of the parent plane with either power, it will be taken into an image, and boom, this is this image right here. It is important to understand, however, that this time this point A prime will not be diametrically opposite to the center of inversion. This point right here, these 2 points are distinct, and one way to see that is as follows. Let's say we take this setup and we rotate our straight line L2 over, let's say, that point A until we straighten it up and make the straight line L2 perpendicular to L1 as we had it in the previous case. What will happen then? Well, our straight line of centers lowercase p will start rotating as well, and then ka-ching, at some point it will click and jump onto the straight line L1 that passes through the center of inversion. And what will happen to the tangents that we draw to the image circle L prime 2 through the points of interest, the center of inversion and the point A prime? Well, they will open up and they will become parallel, because as the straight line of centers P rotates and it wants to rendezvous with the straight line L1, the center of the image circle Q prime will do what? It will jump precisely onto the straight line L1 or L prime 1 as we had it in the previous case. Now, why do we construct the tangent T to the image circle L prime 2 through the center of inversion and the tangent T prime to the circle L prime 2 through the point A prime? Well, precisely because the angle between these tangents and the straight line L prime 1 is what we take to be the angle between the straight line and the circle. And in this case, when we rotate our straight line L2 back into an interesting position, when that angle is neither 0 nor pi over 2, then the straight line of centers will jump off the straight line L1, the center of the circle Q prime will jump off of it over here too, and our previously parallel tangents T and T prime will intersect. Why? Well, they will stop being parallel, and by the same postulate, they will also intersect at the point in the parent plane, and we name that point B. So this is the basic premise, the basic setup. These are the constructive observations that we make in the third and the final case when our straight lines are neither parallel nor perpendicular. This is, again, very straightforward. And again, we run over the same template that I showed in the previous, actually already 3 proofs. So what do we observe over here? Again, we go back and we prove that our favorite tangent T to the image circle L prime 2 drawn through the center of inversion by the same book 1 proposition 27 will be what? Will be parallel to the original pre-image straight line L2. Tangent T to the red image circle L prime 2 drawn through the center of inversion will be parallel to the original pre-image line L2 by book 1 proposition 27. Why is that? Because the tangent, this tangent, must be perpendicular to the radius Q prime O. Q prime O through the, that's the radius we draw through the point of interest over here. That straight line is perpendicular to L2, but now what do we have? We have that exactly that straight line of centers that contains the radius to which the tangent is perpendicular, falls on 2 straight lines, T and L2, in such a way that it makes the alternate angles, for example, this one and this one, or this one and this one, equal one another. Consequently, that the conclusion follows. The tangent T to the circle, to the red image circle L prime 2 drawn through the center of inversion will be parallel to the original pre-image straight line L2. And what do we have now? Well, now we instantly capitalize on that fact, shift things around, and now we'll look at the straight line L prime 1, the green line over here that passes through the center of inversion. Now that straight line does what? In Euclid's tongue, it falls or intersects two parallel straight lines. We already proved that the straight line T and L2 are parallel. Now the straight line L prime 1 falls onto parallel straight lines, and we know that in this case what? Here we already use book 1 proposition 29, that in this case the magnitudes of the alternate angles will be equal. That's the conclusion. Parallel straight lines, alternate angles equal. So for example, this angle must be equal to this angle, but this angle is vertical with respect to this one, so there we go. If we take that the, let's say, angle, the original angle theta, which is neither 0 nor pi over 2 radians between our straight lines L1 and L2 is this, then from this it follows that the magnitude of the angle BOA prime, which is BOA prime, this angle right here, must also be theta. So at one point we already proved that the magnitude of the angle between the images of our straight lines is exactly the same as the magnitude of the angle between the pre-images, the angle theta, by magnitude. You see, theta, theta. Now we just have to show that the same magnitude will be honored, if you will, if we examine the angle between the tangent T prime constructed to the image circle L prime 2 through the second point of contact where our image straight line L prime 1 intersects that image circle. How do we do that? Well, this is where the mechanics of this construction of tangents to a circle through a point on it come in. Here we carefully look at what? We have two angles by construction. This is what I show over here. By construction, the magnitude of the angle Q prime OB and Q prime A prime B, Q prime A prime B must be pi over 2 radians. These angles must be right. Why? Precisely because of how we define what a tangent to a circle at a point is. These straight lines must be perpendicular to the radii drawn, obviously, from the center to the point of interest. O, the center of inversion, O, or A prime. This is evident. Now, next we make the observation that the line segment Q prime B, the line segment Q prime B is shared. See, Q prime B is shared. Why is that? Well, it is shared by what? By the triangles BOQ prime and Q prime AB, which, as we said, are right by construction. Finally, we make this observation over here that because these line segments Q prime O and Q prime A prime, Q prime O and Q prime A prime, this line segment and this line segment are the radii of one and the same circle. By length, they are equal. By length, they are equal. So that means that by the Pythagorean theorem, otherwise known as Euclid's Elements, Book 1, Proposition 47, that means that the lengths of the remaining sides of these two right by construction triangles must be what? They must be equal. The length of the line segment BO must be the same as the length of the line segment BA prime. BO and BA prime must be the same. This is essentially, we're saying that from a point that is located strictly outside of a given circle, the length of the tangents to that circle are one and the same. The lengths are equal. So what does that tell us? Well, that tells us that the triangle OBA prime, OBA prime, the triangle OBA prime, see, we connect them like this, is isosceles, evidently, with the point B, or the vertex B being the vertex of that isosceles triangle. And then if that triangle is isosceles, then by the famous, again, book Euclid's Elements, book 1, proposition 5, Pons Theorem, the magnitude of the interior angles at the base of every non-degenerate isosceles triangle is what is one and the same. That means that the magnitude of the angle BOA prime, BOA prime, this angle, must be exactly the same as the magnitude of the angle BA prime O. BA prime, A prime, O. This angle right here. So that proves, by the way, that proves, so we can write down here again this angle theta. So now we have a beautiful show of angles of the same magnitude, theta, theta, and theta. And that proves that the magnitude of the angle between the original straight lines, L1 and L2, of which exactly one, such as the straight line L1 passes through the center of inversion O, is preserved or is equal to the magnitude of the angles between the images of these straight lines. That is, that magnitude is measured between the straight line, essentially L1, and the circle, the image circle L prime 2, or the angle between that straight line and the tangents drawn to the image circle at the points of interest. One of these points will evidently be the center of inversion, the point O, and the other one will be the second point where the straight line L1 intersects the image circle, or the point A prime, which, by the way, is exactly the image of the point where our two non-parallel and non-perpendicular straight lines L1 and L2 intersect. And that concludes the overall proof of the theorem number 33, and we will move on to the theorem number 34, where now we will peel not only one but both straight lines, the proverbial straight line L1 and the proverbial straight line L2, off of center of inversion, and we will consider what will happen to the angle, to the magnitude of the angle between any two straight lines, none of which pass through the center of inversion. And here again, look at this. If we get to pedantically measure, keep track not only of the magnitude but of the orientation or the direction of an angle. Look, here we measure the magnitude of the angle theta as usual, but the direction, let's say we measure it in the positive or counterclockwise direction. Here at the other magnitude, we have to measure it this way, in the opposite direction. Now, this is it for the theorem number 33, and we will move on to the theorem number 34 next. Lastly, according to the theorem number 34, even when none of any two straight lines pass through the center of inversion, then under the corresponding inversion of the real plane with respect to a circle with any power, be that power positive or negative, the magnitude of the angle between such two straight lines will be preserved. Again, we partition the proof of the theorem number 34 into three distinct parts when the straight lines of interest L1 and and 2 are parallel. The second case when these straight lines are perpendicular. And the third and the final case when these straight lines are neither parallel nor perpendicular. In this segment, we will consider the very first case when the given straight lines are parallel with respect to each other. And in these proofs, I will step a little faster because I will capitalize on the proof that we just constructed for the previous theorem, the theorem number 33. And do not worry if you miss anything. First of all, you can always ask the question. The comment section is open, ask away. And second of all, this lecture is based on my chapter number 7 of my free book, Inversion Geometry for All. The link to that free PDF file that is located in my free GitHub repository is also in the comment section. Click, pop it open in a separate tab in your browser and read along and watch along. As such, when our straight lines L1 and L2 are such that neither one of them passes through the center of inversion O, again, the inversion of the real plane is considered with respect to the circle named C that has the point O as its center, strictly positive real number R as the radius. None of the straight lines pass through the center of inversion. The premise here is that in this case, under the positive and negative power of inversion, the magnitude of the angle between two such straight lines will be exactly the same as the magnitude of the angle between their images. Now, the straight lines, when the straight lines L1 and L2 are parallel, again, based on the previous proof, we take the angle between the magnitude of the angle between these two straight lines to be 0 radians or 0 degrees, and we want to show that when these two straight lines, none of which pass through the center of inversion, this point right here, O, are reflected in a given circle with the chosen power, be that power negative or positive, the angle between these images or the two circles, each of which, by the way, passes through the center of inversion, will also be what? 0 radians, exactly, or 0 degrees. How do we do that? Again, the technology is exactly the same as the technology that we developed in the proof of the previous theorem, theorem number 33. The straight line of centers that is perpendicular to the straight line L1, perpendicular to the straight line L2. We have our nice points. We throw them in. We reflect them in a given circle with the chosen power. We thus lock in the corresponding diameters, cut them in half. We obtain the centers, snap the circles. Everything is wonderful. So that, again, we have to remember that once we do these reflections, we reflect both straight lines in the same power. It is not the case that we reflect one straight line, for example, with negative power, and we reflect the other straight line with respect to the same circle with positive power. No, that is not the case. Once we pick the power of inversion, we stick with it and we apply it to both straight lines. We either reflect both straight lines L1 and N2 with positive power, or we reflect both of them with negative power. In this case, for example, here also we have some variation where the center of inversion can be located in between the pre-image straight lines L1 and L2, or it can be located on one and the same side. For example, when the straight line L2 sits somewhere over here or here, it doesn't matter, when both straight lines are on the same side of the center of inversion. Again, it does not really matter. The argument will remain the same, and that means that the tangency of our points can be what? It can be external as shown over here, or when the straight lines are on the same side of the center of inversion, the tangency will evidently be what? It will be internal, not external, but internal. But again, the argument remains the same. And what is that argument? Well, already based on the previous proof, we show that the angle between two circles will be what? It will be the angle between the tangents drawn to these two circles through the point of interest. Here, in this case, there is only one point of interest, the center of inversion. Thus, we construct the tangents to the circle, the image circle L prime 1. We name that tangent T1, and we construct the second tangent named T2 to the circle L prime 2, shown over here in green, through the center of inversion. And everything that pertains to the first line is shown in blue. And what do we show? Well, using the same technology, straight line of centers, alternate angles are the same, Euclid's elements, book 1, proposition 27, the tangent T1 to the circle L prime 1 at the center of inversion will be parallel to the original straight line L1. T1 is parallel to L1, or L1 is parallel to T1. Likewise, by exactly the same argument, the tangent T2 to the circle L prime 2 through the center of inversion will be what? Will be parallel to the original or the pre-image line L2. L2 is parallel to T2, T2 is parallel to L2. Now we just have to carefully split this technically useful material apart and pick the pieces that we want. Look at this. The idea here is again to use the same book 1 proposition 30. If A is parallel to C and B is parallel to C, then A is parallel to B. Game over. So here, the straight line L1 is parallel to the straight line T1, and L2 is parallel to L1. In other words, we capitalize on our assumption of the case number 1 that our pre-image straight lines L1 and L2 are parallel. So this string of symbols, if we build up this implication, what will we have? Well, we have two straight lines, T1 and L2 are separately parallel to one and the same straight line, L1. Well, by book 1 proposition 30, that precisely this precisely is the conclusion that follows, that T1 and L2 are parallel. T1 and L2 is parallel. And now we grab this result and slug it into another book 1 proposition 2. So now we have T1 and L2 parallel and T2 and L2 parallel from our previous observation. So what is one and the same straight line? It's L2, and we have two separate distinct straight lines, T1 and T2, parallel to one and the same straight line. What is the conclusion? Well, the conclusion is that these two straight lines, T1 and T2, are parallel. Now, when these two straight lines are parallel, again, already we see that the angle between the images of our pre-images is the same. It's 0 radians, but we can make one step further and bring in what our favorite Playfair's axiom and claim that through a given point O, not on, let's say, straight line L1 or L2, they can pass how many straight lines that are parallel to either of these straight lines? Only one. And that precisely means that in this case, the tangents T1 and T2, the tangent to the image circle L prime 1 and the tangent to the image circle L prime 2 is what? It is one and the same, and that is, in some sense, even more so evident that the angle between these two straight lines is again 0 radians, which is exactly the magnitude of the angle between the pre-images in this case, and that proves the first case of the theorem number 34, which states that if any two straight lines L1 and L2 are parallel and neither one of them passes through the center of inversion, then the magnitude of the angle between them, 0 radians, is precisely the same, the magnitude of the angle between their images, between their circles, whether these circles touch externally as shown over here or internally, and again, whether the power of inversion is positive or negative. The second case of the theorem number 34 is so straightforward that it takes actually longer to set it up than to generate its proof. That is, in the second case, we assume that the straight lines L1 and L2 are perpendicular and none of these straight lines pass through the center of inversion. Then, regardless of the power of inversion, be that power positive or negative, our straight line L1 will be taken into the blue image circle L prime 1, and our green straight line L2 shown over here, that is perpendicular to the blue straight line L1, will be taken into the green image circle L prime 2 shown over here. Let the point Q prime 1 be the center of the blue image circle L prime 1, and let the point Q prime 2 be the center of the green image circle L prime 2. Now, what are we trying to prove in this case? In this case, we're trying to prove that the angle between the circles, between these image circles, between the blue circle L prime 1 and the green circle L prime 2 will also be pi over 2 radians or 90 degrees, because this is the magnitude of the angle between our original straight lines. Again, when I say an angle, I usually mean the magnitude of the corresponding angle. And as we defined as we said in definition number 4, the angle between the circles will be the angle between the tangents constructed to these circles at the points of interest. And here there will be 2 points of interest. One such obvious point of interest will be the center of inversion, because both circles pass through the center of inversion. Both of the image circles pass through the center of inversion, the point O. And the second such point will be a distinct point. Let's call it, for example, point P. Now, what do we do here? Well, we construct 2 tangents to these circles at one point, where that is in common to these circles, the point O, and 2 tangents at the second point that is in common to these 2 circles, the point P. Consequently, the tangents to the circle L prime 1 through the center of inversion we call T1. This is this straight line right here. And the tangent to the green circle L prime 2 will be T2 through the center of inversion, these 2 points, these 2 straight lines right here. And the other tangents to these circles we will qualify with the prime. T prime 1 is the tangent to the blue circle L prime 1 through the point P, and T prime 2 is the green tangent to the green image circle L prime 2 through the second point that these 2 circles have in common, the point P. So 4 tangents all together, and once we have this set up, we will see that the tangent T1 in this case, well, let us take this step by step. Again, through exactly the same reasoning that we used in the previous cases, we showed that the tangent T1 to the circle L prime 1 through the center of inversion will be parallel to the pre-image straight line L1. Likewise, by exactly the same reasoning, book 1 proposition 27, a straight line falling on 2 straight lines making alternate angles equal, the straight lines are parallel. The tangent T2 to the green circle L prime 2, this tangent right here, this tangent through the center of inversion will be parallel to the straight line, to the original pre-image straight line L2. Thus, these 4 straight lines, blue L1, green L2, and in some sense they should have been blue T1 and green T2, form what? Exactly, they form a parallelogram. And as Euclid proves again in his first book of Elements, in parallelogrammatic areas, the magnitudes of angles that are opposite of each other, they are what? They're equal by magnitude wherever they are. In our case, the magnitude is known, pi over 2 radians or 90 degrees. So this angle right here, vertical, we take, let's say, this angle to be the magnitude of the angle between these 2 straight lines. consequently the angle at the vertex O. I do not want to throw more letters at this diagram than I have to. Let's keep it simple. We'll all understand that the magnitude of the interior angle at the point O from here to here is the same one, pi over 2 radians. Now, the last thing, as we showed in the previous theorem, in the proof of the previous theorem, the theorem number 33, again, the proof is very straightforward. Let's say we take our tangents drawn to the circle L prime 1. They will pass this time through the center of the other circle, Q prime 2, and by the corresponding angles, that must be right. The angle between the tangent and the radius, for example, Q prime 1P and Q prime 1O, these angles must be right. The triangles are right. The shared hypotenuse I did not show. By the Pythagorean theorem, the lengths of the remaining sides must be equal. Here, the lengths of the sides are the same. They're the radii of the image circle L prime 2. So the length of the line segment Q prime 1P is the same as the length of the line segment Q prime 1O. So the bottom line is that the triangle, in this case, what is it? O Q prime 1P will be isosceles. This length is equal to this length. And by the same argument, if we step into the point Q prime 1 and look at the lengths of the tangents to the circle L prime 2 here, we will also prove the same thing. Shared hypotenuse equal angles by magnitude which are right triangles. The remaining sides must be equal, and there you go. The triangle OQ prime 2P must be isosceles. Q prime 2P is isosceles. So when I wrote alpha equals alpha, this is basically my shorthand notation to say that the angles or the magnitudes of the angles at the base of every non-degenerate plane Euclidean triangle must be equal one another. So there we go. This angle is equal to this angle, and this angle equal to this angle. So this must hold at both points, at both vertices, O and P. And that means that alpha plus beta at the point O must be the same as alpha plus beta at the point P. So the magnitude of the angle Q prime 1 P Q prime 2, this angle right here, let's see if I can show it convincingly to you guys so you can see it. This angle right here from here to here must be also right, which is the angle between these two straight lines. There you go. That proves that at both points, the angle between the image circles, the image circle, the blue image circle L prime 1 and the green image circle L prime 2, by magnitude is pi over 2, which is exactly the same magnitude. That is the formed by the angle between the straight lines L1 and L2. And now we just have to cover the third and the final case when our proverbial straight lines L1 and L2 are neither parallel nor perpendicular but form some interesting angle. Try to think on your own what will change over here. Not much. The proof in essence will be the same, but we will cover that proof in the next segment. The third and the final case of the theorem number 34, when the straight lines L1 and L2 are neither parallel nor perpendicular with respect to each other, and none of these straight line passes through the center of inversion, is only marginally different from the previous case when our straight lines were perpendicular. That is why I purposefully did not erase the diagram for the case number 2. It is shown on the left side of your screen, and the third case is covered on the right. side of your screen for the ease of comparison, and what is the small and subtle but not really that important of a difference between the two cases. Well, there is actually an official name for this arrangement of circles, and in this case, because the angle between the circles is pi over 2 radians, as we proved, these circles in this case are called orthogonal, and we will actually study in the near future precisely what happens to orthogonal circles under the inversion of the real plane with respect to a circle. This is actually quite interesting. We will prove a couple very useful theorems, but in the case when the straight lines L1 and L2 are neither parallel nor perpendicular, and they form some interesting angle theta as shown over here, we pretty much repeat the previous proof of the case number 2 verbatim. We still have our tangent T1 parallel to the original pre-image straight line L1. We have the tangent T2 parallel to the pre-image line L2. Again, we construct the tangent T1 to the circle L'1 through the center of inversion, and we construct the tangent T2 to the image circle L'2 through the center of inversion as well. And using the argument that we just constructed in the previous case, we show that these two four straight lines, the original straight line blue L1, green L2, the which one, the tangent T1 and the tangent, where is it, T2, this time it's this one, you see this one, this tangent, this one, they form what? They form again a parallelogram. What are the vertices of this parallelogram? Here, 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 at the center of inversion, and right here. And again, by the corresponding theorem, the magnitudes of the opposite angles, of the magnitudes of the interior and opposite angles in all non-degenerate parallelogrammatic areas, whatever they are, equal one another. In the previous case, the magnitude of this angle was what? Pi over 2 radians on 90 degrees. Now it's not. It's some angle theta, but still this angle must be equal to this angle. Game over. So what we just proved? We proved that the magnitude of the angle between our pre-image straight lines L1 and L2 is equal to the magnitude between their images at the point O, at the center of inversion. So now we have to prove the same for the other point over which our image circles intersect. Again, I call that point P over here. That was the point P over here. So at this point, what is the subtle difference? Well, the subtle difference is the following. In the first case, when the circles are actually orthogonal, their tangents to these two circles intersect precisely at the centers of the corresponding circles. The tangents to the circle L'2 intersected at the center of the circle L'1, and the tangents to the circle L'1, this one and this one, intersected where? Intersected at the center of the image circle L'2. Here, however, this will not happen because the circles L'1 and L'2 are no longer orthogonal. These tangents to these circles will intersect still on the straight line that connects the centers of these two circles, on the straight line Q'1 and Q'2 at the points A and B. But these points A and B will be distinct from the corresponding centers of our image circles. In this case, these points coincided with the centers. You see, this point and this point. So in some sense, the point A is sitting right here, and the point B is sitting right here. It's hiding, it's lurking in there and waiting for an opportunity to show its face. And boom, the moment the circles at hand are no longer orthogonal, they show up loud and clear, A and B. These are the points where the tangents to our circles intersect. Still, this doesn't change anything in a fundamental way. We still go by the fact that we have right triangles Q prime 1 OB, Q prime 1 OB, precisely because this is the tangent by definition. It has to be perpendicular to the corresponding radius, so this angle is right, and correspondingly the triangle is right, and the triangle Q prime 1 PB is also right because the corresponding angle at P must be what? Must be right. So the shared hypotenuse Q prime 1B, right triangle by the Pythagorean theorem, the remaining sides must be equal. So the length of the line segment BP must be the same as the length of the line segment BO. The corresponding triangle OBP must be what? Isosceles. This length is equal to this length. Correspondingly, again, beta equal to beta. I showed over here these angles are the same. These angles are the same by exactly the same argument. If we flip this argument and repeat it for the triangle OAP, again, we will prove exactly, we will construct exactly the same proof. We will have, for example, the angle OAQ prime 1 will be what? Will be right over here because precisely this is the tangent to our green image circle L prime 2. Likewise, we prove that the length of the line segment AP must be equal to the length of the line segment AO. Consequently, the triangle OAP also must be isosceles, so the magnitudes of the angles at the base of every non-degenerate Euclidean triangles must be the same. This time it's the angle AOP and APO. My diagram here is a little bit too small. I decided not to show, but you understand that these angles are alpha now. These are the analogs of these angles, alpha. So either way, this angle right here is a composite quantity. We prove that this angle by magnitude must be theta, and it is comprised of the magnitude of the angle beta and alpha. So alpha plus beta is theta. Boom, it must hold true at either vertex O and P. Consequently, the angle between the image circles, blue circle L prime 1 and L prime 2, the green one L prime 2, at the point P is also by magnitude. That angle must be equal to the angle between the circles, these two circles at the point O, which is the magnitude of the angle between our two straight lines L1 and L2, which are neither perpendicular nor parallel. And that concludes the proof. Again, if you think you missed anything or something is not clear, I did not show you. If you think that something is missing, please let me know in the comment section. The comment section is open. Here we will have another line segment. I did not show it, but this concludes all the cases. This encompasses all the cases for the theorem number 34, and we can move on to the theorems number 35 and 36, which I will only state but do not prove. According to the theorem number 35, under the inversion of a plane with respect to a circle named C that has the point O as its center and a strictly positive real number R as its radius with either positive or negative power, the magnitude of the angle between a straight line and a circle is preserved. We will not be proving this theorem because the proof of this theorem, in a sense, follows directly from the proofs of the theorems number 32, 33, and 34, because in all these cases, in all the interesting cases, all the meaningful cases when the angle between a straight line and a circle can be meaningfully defined, all these cases are reduced to precisely the case of the magnitude of the angle between two straight lines, and we covered all these possible cases. For example, when a straight line in question and a circle have precisely one point in common, we say that in this case these two geometric objects touch each other at that single point, then evidently the angle between the straight line and the circle will be 0 degrees in some sense. However funny that may sound, the circle is parallel to that straight line, and when a given straight line and a given circle have precisely two distinct points in common, and in this case these two objects genuinely intersect, then again the angle between such a straight line and such a circle is reduced to the angle, or the magnitudes of these angles are reduced to the magnitudes of the angles between two straight lines, and we covered all the possible cases in the previous theorems already. According to the theorem number 36, under an inversion of a plane with respect to a circle named C that has the point O as its center and a strictly positive real number R as its radius, be the power of inversion positive or negative, the magnitude of the angle between any two circles, these times circles, is preserved. The magnitude of the angle between the circles is preserved as well. Again, we will only formulate this theorem. We will not prove it, because the proof of this theorem follows from the proofs of the theorems 32, 33, and 34, because in all the meaningful cases, the question about the magnitude of the angle between any two circles can be reduced in a meaningful way to the question of the magnitude of the angle between the two corresponding straight lines, which are the tangents constructed to the circles through the points of interest. That is, here I will leave you with a question and some food for thought. When two circles touch, when they have precisely one point in common, and the circles can touch each other externally as shown over here, or they can touch each other internally, let's say this way, then it is a meaningful situation when we can introduce the notion of the angle between two circles. In this case, we will say that these two circles are parallel in some sense, because the angle between the corresponding tangents will be 0. When two circles have precisely two distinct points in common, or they genuinely intersect, being quadratic curves, they intersect over two distinct points, then again the question about the angle between these two circles can be meaningfully answered. We reduce the answer to the question to the magnitude of the angle between the corresponding tangents constructed through all the points of interest in this case. That is fine. Now, when two circles are juxtaposed against each other in such a way that one circle is completely contained within the other, and the circles have otherwise 0 points in common, which includes the case when the circles are concentric, it doesn't seem to be possible to meaningfully define the notion of the angle between such two circles. Yes, no, maybe. Likewise, when the two given circles have precisely 0 points in common, but they are positioned one outside the other, as shown over here, then it is possible to construct, and we already went through this exercise, how many tangents? Well, two external tangents and two internal tangents. Here the external tangents are shown in blue, and the internal tangents are shown in orange. What do you think? Is it possible in this case, for this specific configuration of two circles, is it possible to meaningfully introduce the notion of the angle between two such circles? What do you think? Leave us your idea in the comment section. The comment is open, but meanwhile, this is it for the episode 8 and lecture 8. And in the next episode, episode 9, lecture 9, we will look at how inversion of the real plane with respect to a circle acts on the points of tangency between two interesting objects. We will also look at the radical axis, and we will look at the notion of the power of a point with respect to a circle.